Hi, welcome back to General Chemistry 1. This is Dr. Fang Xu. Today we're going to talk about our last chapter, chapter 11. So the topic is valence bond theory and orbital hybridization. So first, what is valence bond theory? Valence bond theory is that a covalent bond forms when orbitals of two atoms overlap and a pair of electrons occupy the overlap region. So for example, here, for the hydrogen, each of them have the 1s orbital. And when these two 1s orbital overlap and they are unpaired electrons to form from each atom to form a paired electrons here in the overlap region, then they form a bond and we have this hydrogen bond. The same thing with hydrogen fluoride. Instead of the two 1s orbitals, we have 1s orbital from hydrogen and 2p orbital from fluorine. And again, they're a section of the overlap and is occupied with a pair of electrons contributed by the two atoms. We form a covalent bond here as hydrogen fluoride. And also in the fluorine, two fluorine gas here is the same. So they are the overlap of the 2p orbital of fluorine. So when we form this bond from the valence bond theory, we need to pay attention to a few points. First, the electrons from each atom should have the opposite spins before pairing, and after, once they have the opposite spins, they can pair up to form an electron pair to form a bond. And also for these bonding orbitals, they need to have the maximum overlap of bonding orbitals. So in other words, the HF bond, you can see the overlapping is very nicely done here. But if the 1s orbital is reaching the node of this 2p orbital of F, it's not a good overlapping. Okay, so finally, we move on to the topic of a hybridization of atomic orbitals. And we need to hybridize the atomic orbitals, that is to meet the shape from VS-EPR theory. So let me just give you an example. In the boron trifluoride, from the VS-EPR theory, we know it has a planar trigonal planar shape. Okay, if you look at the valence electrons in boron, it has two electrons in the 2s orbital and 1 electron in the 2p orbital. The shape of the s orbital is like this, a sphere shape. And the p orbital has three different orbitals, three different directions along the x, y, and z. So along any of them together, it does not give us a good orbital pointing to the three vertices in the trigonal planar shape. So what can we do? We can mix up this s and p orbitals so we can generate a new set of orbitals. We call it hybridized orbitals. So hybridized orbitals to create a new set of orbitals that can meet the shape of a molecule. So that's why we need orbital hybridization. Because of the limited numbers of s and p orbitals, we only have certain combination of orbital hybridization. And this is summarized in table 1.1. So it gives you the hybridization of orbitals and also the corresponding orbital shape. So what you need to focus here is the hybrid orbital formed. If we have 1s and 1p orbital, we form the sp hybridization. We have a linear shape of the orbital, hybridized orbital. If we have 1s and 2p orbitals, so we have the sp2 hybridization, it's a trigonal planar. If it's sp3 hybridization, it's a tetrahedral shape. If it's sp3d hybridization, it's a trigonal bipyramidal shape. If it's sp3d2 hybridization, we have the octahedral shape. So we only have this in this general chemistry 1, you only need to know this 1, 2, 3, 4, 5 different types of orbital hybridization. Okay, so if we can link the orbital hybridization to the VS-EPR theory we have before, you probably already find one thing, that if you count how many orbitals are there in total for each orbital hybridization, the sum of them match the electron groups you find in the VS-EPR theory. So For the sp orbital hybridization, we have two orbitals, 1s, 1p. So in total, we have two groups, and that's a linear shape corresponding to two electron groups in the VS-EPR theory. The same for sp2, 1s plus 2p orbitals, in total three orbitals, three hybrid orbitals, and that corresponding to the three electron groups in the VS-EPR theory. That's a trigonal planar shape. The same with tetrahedral, trigonal bipyramidal, and octahedral shape. So if you count how many orbitals involving in the hybridization, that number corresponding to the electron groups in the VS-EPR theory, including how many atoms around central atoms and how many pairs of electrons around central atoms. So that makes us make these two knowledges closely linked to each other. And from that, we can determine the orbital hybridization from the Lewis structure from the VS-EPR theory. So here is an example, the summary of the table with the example of molecule formulas, its corresponding Lewis structures, its VS-EPR class or VS-EPR designation, and orbital hybridization. So as I said, the sum of the electron groups in the VS-EPR equals to the sum of hybrid orbitals. So as AX2, we only have two electron groups. So we have S and P, two orbitals involved. Take another example, AX2E2, we have 2 plus 2 that equals to 4 electron groups near the central atom in the VS-EPR. Then when we have 4 orbitals, we do sp3 hybridization to have 4 orbitals in total to meet with the VS-EPR theory. Okay, so that is if a molecule has AXMEN and SP sub X D sub Y, then we will have N plus N equals to 1 plus S plus Y. That one is a subscript of S orbital, so that's 1. Yeah, so with that, we have a few steps to determine the hybridization of the orbitals. So first, of course, write the Lewis structure, so we can determine the sum of M and N, right? That is the second step, get electron groups in the VS-EPR, the sum of M and N. And then from that, we can identify the hybridization. Okay, how many orbitals are involved in this hybridization? So S always has 1 as a subscript, and we leave that out. And if you have numbers to fill in, we start to use p orbitals first. So, and at most we have 3 p orbitals. In other words, the subscript of p can have a largest number of 3. It can be either 1, 2, or 3. Okay. And if we still need more numbers, we start to involve the d orbital. Okay. So, and for the scope of general chemistry 1, we can only have sp3d and or sp3d2, either case. Okay. So the rest of this video, I'm going to introduce how does this hybrid orbitals look like, and I'll give you a few examples of molecules and see how it looks like how to visualize these orbitals, these hybridized orbitals. Okay, so first is sp and sp2 orbital hybridization. The sp hybridization makes 1 s orbitals and 1 p orbital within the same shell, the same principal quantum number. So for example, if we have beryllium chlorine, so we have 1 beryllium and 2 chlorine, it's a linear shape, and then we need 2 orbitals, right? So for 2 orbitals, we have 2s and 2p, mix them together to have 2 sp orbitals. So the number of mixed orbitals equals to the original number of orbitals we use. But because if we do that, the paired electrons in the 2s now becomes 2 single electrons in the sp orbital. So that makes us available for bonding. And then this will be how the beryllium chloride look like. So the sp orbital becomes a linear shape, and then the size is slightly different from s or p orbitals, and each of the electron here can bond with the single electron from chlorine to form this chemical bonds. Okay, So then sp2 hybridization, the same concept, but in this case, we're using one s orbital and two p orbitals. If we have one s and two p orbitals, all three orbitals together, we can have three sp2 orbitals. And then again, we need to redistribute the valence electrons from the 1s and 2p, the two 2p orbitals. So now we have three unpaired electrons here in boron. And in the boron trifluoride, the sp2 hybridization will give us the trigonal planar shape. And then the lone electrons in the sp2 orbitals can use to pair up with the fluorine and form this boron trifluoride molecule. Please pay attention that these valence electrons are redistributed in the hybrid orbitals. We're not using more valence electrons or less valence electrons from the orbitals contribute to the hybridization before, but we just need to redistribute them. Okay. Now let's take a look at sp3 orbital. We use one s orbital and three p orbitals within the same shell, same principal quantum number. So, and that is, we used up all the p orbitals and s orbitals. So we have the sp3 hybridization, and then we have this tetrahedral shape. Okay, so for these hybridized orbitals, it can be used for bonding, like this ammonia, the sp3 bond with hydrogen, or it can be occupied with a pair of lone electrons. Okay, a pair of electrons here. So these sp3 here does not bond with with hydrogen. Instead, it's occupied with lone electrons, a pair of electrons. Also, we can have the sp3 hybridization for water molecule. Instead of the lone pairs here occupying one hybrid orbitals, we have two hybrid orbitals occupied by lone pairs. So you can determine how many lone pair electrons here, either through the Lewis structure you draw or through this hybrid orbitals. You can see how many electrons originally you have, and after redistribute them in the hybrid orbitals, how many of the electrons form the pair. And each pair here is called a lone pair. Okay, electron redistributed in the hybrid orbitals. And then sp3d. Now we're involving not only s and p orbitals, we still need to involve 1d orbitals. And all of these orbitals should be in the same shell. An example here is chlorine trifluoride. Okay, so from the Lewis structure, we know it has a trigonal pyramidal ideal shape. Okay, so that includes the two lone pairs from chlorine. But anyway, it has 5 different electron groups around it, 3 atoms, 2 pair of electrons. So we need to have 5 orbitals in total. We used up 4 orbitals as s and p orbitals. We're still lacking 1, so we're using 1d orbitals. Mix them all together to have this hybridized sp3d orbitals. Redistributed all the electrons, so we'll have 2 lone pairs and 3 bonding electrons from the chlorine. Okay, and then we form the structure which agrees with the VS-EPR theory. Also, we may have the phosphorus pentachloride. So in this case, there are 5 different groups to the phosphorus. So if we, like before, remix this 1s orbital, 3p orbital, and 1d orbital together, originally we have 5 valence electrons, redistribute them into this hybrid orbitals. We have 5 single spin electrons. Okay, then we can use this 5 electrons to bind with 5 different chlorine atoms to form the phosphorus pentachloride. Okay, so when you distribute electrons in the hybrid orbitals like before, these electrons also want to occupy as many orbitals as possible in the same energy. So if we have 5 electrons before, now these 5 electrons will occupy 5 different orbitals. All right, and finally we have sp3d2. That means we need 1s, 3p, and 2d orbitals within the same shell for this orbital hybridization. So the example here is SF6 sulfur hex fluoride. Okay, so we just again one more 3D orbitals here. In total, we will have 6 hybrid orbitals. Redistribute electrons here so they can occupy all of the 6 hybrid orbitals. So each of this hybrid orbital can form a bond with fluorine to form this sulfur hex fluoride molecule. So the valence electrons are redistributed in this hybrid orbitals. And for you, when you work with this hybridization problems, usually it will just ask you what is a hybridization it is. How many orbitals are involved in this hybridization, and determine what the orbital hybridization is. Following the 3 previous steps I mentioned, and you should be good. And it's so closely related to the VS-EPR theory in chapter 10. So I highly recommend you connect these 2 knowledges together. So don't separate them. They're all together. They all agree with each other very well. All right, and I'll see you next time. Bye.